Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is Lecture 5, Part 3, and Video 15. We are going to continue talking about the maximum likelihood estimator, and we're going to use the log likelihood function to find the MLE for both the mean and the variance of the normal distribution. So why don't we go ahead and get started. This is the normal distribution. Again, very important. You need to know how to do this. You can bet that on a test there will be something that's different than this but similar. Anyway, you'll need to understand and make sure you know how to do this. And we're using two parameters. Remember, we have the mean and the variance for the normal distribution. So we're going to say that these random variables are a random sample because they're IID from the same distribution. X with, now I'm going to say theta 1 and theta 2. So mu is equal to theta 1 and sigma squared is equal to theta 2. So you got to be very careful here. This doesn't have a square. And since we've given you this without the square, we've identified the problem. You can't make it squared. If you make it squared, you're not solving the problem correctly. So be very, very careful. Okay? So when we define a parameter, we have to be very careful to make sure that we're not squaring something we shouldn't square, etc. Okay, so they are distributed as this PDF, and since it's the normal distribution, this is how we can write it in terms of theta 1 and theta 2. So remember that we normally have 1 over sigma square root of 2 pi e to the negative x minus mu quantity squared over 2 sigma squared. And so we're substituting in theta 1 and theta 2 into this. Well, the mu is an easy substitution directly there. Let me get rid of that. And then we have sigma squared, that is theta 2. So that's a direct substitution here. It's not squared. It's just theta 2. The trickier part is that we have here, this is equal to the square root of theta 2. So that's why we've put theta 2 under the square root with the 2 pi here, okay, because of the way we've defined it. So please take a moment to make sure that you understand what's happened there with these substitutions. Don't just gloss over it because it will bite you later, so to speak. Okay, and then since it's a PDF, we have to put in x, and we should also put in mu as any real number, and sigma squared is positive, not 0. If it's 0, then we're dividing by 0 here, and we can't have that, okay? So I probably should reverse this and say sigma squared is greater than 0. All right. So again, theta 1's the mean, theta 2's the variance, and so our parameter space is sigma, and we could just write theta for these two, okay? A lot of people will just write theta such that theta 1 is, well, they wouldn't write it here, but in L, they often just write theta for this vector. We went over that in a few videos ago. And it's theta 1, the set of the pair of theta 1, theta 2, such that theta 1 is between negative infinity and positive infinity, or you could write theta 1 is in the reals. That's okay too. And then we've got theta 2 is between 0 and infinity, or you could just write theta 2 is greater than 0. That's okay too. Okay, they're equivalent, and it's fine notation. So whichever one you prefer, as long as you use it correctly, I'm okay. Now we want to find the MLE of both theta 1 and theta 2. So this is a multi-dimensional parameter space, or a vector. The parameter space is a vector space. Okay, and so we have we're going to have to take derivatives for theta 1 and a separate derivative for theta 2. We'll have two equations with two unknowns. We're able to solve that. If it's solvable, we can solve it for a single value, if it is, and as long as they're independent of each other. And we've proven that mu and we've proven that x bar and s squared are independent last semester. So we'll see that we could prove that mu and sigma squared are independent of each other. So I believe that's a correct statement. don't take me to the bank on that. All right, I need to check it. All right, so let's look at the, I'm going to zoom in here, and I want to write the likelihood function, L of theta 1, theta 2, is equal to, and this is the product of f of xi, theta 1, theta 2, or I could just write this as f of xi theta, remember, and let theta represent the vector. I'm not going to do that. I'd like to be a little more specific in this class for you, but you could do that and I'd be fine with it, okay, as long as you do it correctly. And so this is equal to I equals 1 to n, and so I have 2 pi theta 2, that's under the square root and in the denominator, times exp, and then negative xi minus theta 1 squared over 2 theta 2, okay? And I'm not done, so I'm not going to put anything else right now. I'm going to expand this so that we can see what it is. But before I do that, I want to point out that 1 over square root of 2 pi theta 2 is equal to square root of 2 pi theta 2 to the negative 1, which is equal to 2 pi theta 2 to the 1/2 raised to the negative 1, which is, I'm doing this in great detail, but just to help you out with the thing. Remember, the square root is a 1/2 power. So then I multiply exponents, and that's 2 pi theta 2 to the negative 1/2. All right? So that's how I like to write this in exponents. Why? Because when I do a product, I'm going to get an exponent. When I take the derivative, it's a lot easier for me to use a negative exponent in the derivative than it is for me to see a fraction and then have to think about it. Or maybe somebody would be tempted to use the quotient rule, and that is a really, really bad idea. That makes it so complicated. I would avoid that at all costs, okay? If you can. And we can, so I'll show you how. All right. So knowing that I'm substituting in this, now if I take this n times and multiply it by itself n times, there's no indice here. There's no I. So they're constants. So this is going to be 2 pi theta 2 raised to the negative n over 2. We're raising it to the nth power, or multiplying it n times itself n times, so it's going to be n times negative 1/2, that's negative n over 2. And then we have, this is the equivalent of e, remember, e raised to the negative xi minus theta 1 divided by 2 theta 2. So we multiply xi, so I'm going to write this out. So let's not write it like this yet. Let's write it out, each term, or several terms. So I've got 2 pi theta 2 to the negative 1/2 exp negative x1 minus theta 1 squared over 2 theta 2 times 2 pi theta 2 to the negative 1/2 exp to the negative x2 minus theta 1 squared over 2 theta 2 ... up until we get to n. And so this is going to be 2 pi theta 2 to the negative 1/2 exp negative xn minus theta 1 quantity squared over 2 theta 2. Okay. And so I've got n terms. I've got this repeated n times. So I've got it times itself n times. And so 2 pi theta 2 to the negative 1/2 raised to the nth power, I multiply the exponents. So this is going to be, not negative, it's going to be, let's zoom in, 2 pi theta 2 to the negative n over 2 exp. Now that's an exponent, it's the same base, so I'm going to add everything in the square brackets together. They have a common denominator, 2 theta 2, all of them, and there's n of them, and so it goes from x1 up to xn, and I'm summing, but there's a square here, so I can't get rid of anything or combine anything or make anything any simpler, it's going to be the sum of xi minus theta 1 quantity squared over 2 theta 2. Now let me get rid of this extra over here so it doesn't confuse us. I need to be a little more careful with that. All right. And did I change this back? No, I need to change it to small so I don't over erase when I'm ready. Okay, so this is, and now that I've got the likelihood function, I need to put in about the parameters, and so I can say theta 1, theta 2 in, I could just say sigma, where sigma's been defined up here. That's okay too, okay? But say something. This whole thing is the likelihood function. You can write out sigma again, or you can just say that they're in sigma, okay? So I would hope you'll write it out again just because this is new to you, okay? So that you keep it straight. All right, so that's the first thing I need to do. Now I need to find the log likelihood function. So when I say, I could just say L of theta, and I could just say little l of theta here. But I am writing it out in detail so that we know that there's two of them, okay? So this is going to be, I've got two terms multiplied by each other. I've got the term in the front here, and then I have this exponent term, okay? So I'm going to take the log of two products. So it's going to be the sum of the logs, right? Switch back, and maybe I'll leave it green, stand out a little bit. Okay, so this is going to be log of this. I can take the exponent using the property of logs and bring it out in front of the log. So this is going to be negative n over 2 log of 2 pi theta 2. Now, you certainly could break this up into sums of logs. Don't forget your constant in the front for each and every one of them, okay? I'm not going to do that. I find that it just makes it too messy and too big. So I'm going to keep it like this, and I'll just use the chain rule when I take the derivative. So now it's a plus, and I have a log base e of e to this exponent. That's what's in the brackets. So remember that I'm just going to end up with what's in the brackets. And so this is going to be actually a negative. It's negative, so I'm going to go ahead and put a negative here. Sum of xi minus theta 1 squared over 2 theta 2. Okay, so that's my log likelihood. And again, I'll say theta 1, theta 2 in sigma. And so this whole thing in green is my log likelihood function. So to be proper, we're going to make sure that we specify the parameter space, okay? Now, in this, so now we need to take the derivative, and we're going to have to take two derivatives. So we're going to take dl d theta 1, and so this is going to equal, I don't have a theta 1 in this term, so it's going to end up being a 0. 0. Minus. Now, I need to take the derivative with respect to theta 1 in the second term. So here's the denominator is just a constant. I could pull 1 over 2 theta 2 out to the front, and now I'm taking the derivative of that summation. Well, the derivative of the sum is the sum of the derivatives. So you should know that the derivative, f of x plus g of x, use your brackets so it's not confusing, is equal to, that's the derivative of the sum. So I could rewrite this, maybe it'll make better sense if I write it like this, f1, f2, etc., right? And so let me expand this out. So I can write this plus f of 3 of x plus fn of x. And so this is d dx of the sum of fi of x. Well, we know that this is equal to f1 prime of x plus f 2, nope, down here, 2 prime of x plus dot 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 fn prime of x, which is equal to the sum of f of I prime of x. So the derivative of the sums is the sum of the derivatives. So we can basically take the derivative inside the summation sign here. That's what I'm saying when I'm saying that. Okay? And we learned that in Calculus 1, but I know that you may not have realized that it extended to these summation signs. I hope you have. I hope you've had Calculus 3, but maybe not. All right. So this is going to, so I'm going to take the derivative of the sums, so that's going to be the sum of, that's going to be the sum of the derivative, and that's going to be 2 xi minus theta, now 1, and it's with respect to theta 1, I have to use the chain rule on this, so it's going to be a negative 1, because with respect to theta, xi, derivative with respect to theta of xi makes xi a constant, so it's a 0, 0 minus 1, or a negative 1. And then we have the 2 theta out there. Okay, so, all right. So this is going to be, I've got a negative, and this is going to be a negative 1. So I've got a negative, negative, it's a positive. So this is sum of 2 times sum of xi minus theta 1 over 2 theta 2. And I'm going to set this equal to 0. And remember, we're solving for theta 1. Right? And so with this, this becomes, so this is it. And so I can multiply both sides by this 2 theta 2 because it's not the variable that we're looking for, right? We're solving for theta 1. So I end up with 2 sum of xi minus theta 1 is equal to 0. Okay, yep. And now a constant, I can divide both sides by 2, and so the 2 goes away, right? It just becomes a 1. 2 divided by 2 is 1, and that's still, so I'm left with this. Now, be careful. Remember, you've got a summation here. So I'm going to rewrite this a little neater, hopefully a little smaller. So I end up with the sum of xi minus theta 1 is equal to 0, and that's the same thing as the sum of xi minus n theta 1 is equal to 0. And then I solve for theta 1, so I have n theta 1 equals to the sum of xi. Theta 1 is equal to the sum of xi over n equals x bar. Awesome. Okay. Now, I'm going to go ahead and take, so this should be my MLE. As long as it's a maximum, it should be my MLE. Now, if you looked at the normal distribution, you'll notice that it's a concave up, but that doesn't help us because that's in terms of x. We'd have to plot it in terms of mu, or in this case theta 1, to see the shape. Is it concave up, concave down, or does it oscillate, or what have you? And that's the only way we could just look at it and tell that this is a maximum. So with a computer, that'd be easy to do, but by hand, it's not. So let's do the second one. So we'll have to check this with the second derivative test. Or we could use the first derivative test, but I think I use the second derivative test. In fact, I'm going to go ahead and do that. I didn't realize I went ahead and did that in my notes. So we're going to take dl squared, right? That's what we do, yeah. D squared L over D theta 1 squared. I always get those notations mixed up a little bit. And so I have this as that. In fact, I had 2 here, so these 2's cancel, don't they? So those 2's, the 2's canceled there. And so now, remember, it doesn't hurt to have the theta 2 there, right? It does not hurt to have the theta 2 there because it's a constant with respect to theta 1. I can pull it out, 1 over theta 2. And then I'm going to take the derivative of the theta 1 of the sum of xi minus theta 1. And so this is 1 over theta 2. And then I have the derivative of, remember, I can take it inside the summation, the sum of 0 minus 1. Okay? And so this is equal to negative n over theta 2. I've got n of these. This is negative 1. I've got n of them, so negative n over theta 2. Theta 2 is greater than 0. So this is always positive, and n is greater than 0, or you don't have a sample. So this is always negative. So negative divided by positive is always negative. So I'm doing that just to kind of show you what I'm saying, but this is negative n over theta 2 is always going to be less than 0. Therefore, theta 1 hat equals x bar is the maximum by the second derivative test. Therefore, theta 1 hat equals x bar is the MLE of theta 1. So that portion of the proof is proved. Okay, now we do theta 2. So now I need dl d theta 2. And so I need to CL. So I've got the first term now has a theta 2 in it. Okay, so I have negative n over 2, and then I take the derivative of the log, and that is going to be 1 over 2 pi theta 2, but I have to use the chain rule on what's inside the function. So the derivative of that with respect to theta 2 is just going to be 2 pi, right? So let me get rid of the circle. So times 2 pi. So this 2 pi and this 2 pi cancel out, and I'm left with negative n over 2 theta 2. Okay, so I don't need to, I'm sorry, I don't need to do that part yet. So those cancel out, but I need to do the second term, okay? And the second term here, the second term, oops. So the second term is here. I need to take the derivative of that with respect to theta 2, okay? So to do that, I'm going to say plus, because was this plus? It was a, yeah, I'm sorry. I need to do L. So I'm looking at the wrong one. I need L, not, so the second term of L is here. So that's a negative, okay? So this is going to be negative. And then the numerator is a constant. So this is sum of xi minus theta 1 quantity squared. That doesn't have a theta 2 in it. And I have, so I can rewrite this as 1/2, and then I've got theta 2 to the negative 1, but I need to take the derivative of this. So that's what I need to do here. If I rewrite, let me be careful. If I rewrite this as 1/2 sum of xi minus theta 1 squared times theta 2 to the negative 1, okay? So that's how I like to write it if I'm going to take the derivative. So I have a 1/2 out here. So I minus 1/2. And then I have sum of xi minus theta 1 quantity squared. And then I take the derivative of this, and I have a negative theta 2 negative 2 to the negative 2. Okay. So now I'm going to go back. I'm going to go to black now. And I've canceled out here. This is going to give me a negative n over 2 theta 2, and I've got a negative and a negative, so this is going to be a positive, so you can see it's really important to keep these signs straight. And then I have sum of xi minus theta 1 squared over 2 theta 2 squared. So negative n, sum of, yep. Now what I'm going to do is find a common denominator. So it's going to be this. Okay. So this is equal to, now I need to multiply top and bottom by theta 2 in order to get a theta squared on the 2 theta squared on the bottom. So this is going to be negative n theta 2 plus sum of xi minus theta 1 quantity squared over 2 theta 2 squared. And I need, this is the first derivative, so I need to set this equal to 0. Okay? All right. Okay, so this is always greater than 0. So to get this to 0, that leaves me with the numerator. Always positive, always greater than 0. So key is numerator. Okay? I need to set this numerator equal to 0 in order to make the whole thing 0. 0 divided by a positive number is 0, right? Okay, so let's clean this up. Now, so then I need my numerator, sum of xi minus theta 1 squared minus n theta 2 equals 0. So now I don't have any theta 2's over here, so this time I can add this to both sides with no issue because I'm not going to end up canceling out that by a solution by accident. So this implies that n theta 2 is equal to the sum of xi minus theta 1 quantity squared, which implies that theta 2 is equal to 1 over n sum of xi minus theta 1 squared. Okay. Now I substitute in theta 1 hat. 1 over n sum of xi minus theta 1 hat, which is x bar squared. Okay? And so this is, I shouldn't just circle that. So that's my answer. Now I need to check if max. So I'm going to take d squared L d theta 2 squared. So I need to find a good expression for that. And I think I'm going to use this here and rewrite it as negative n over, let's see, negative n over 2 theta 2 to the negative 1 plus sum of, so I'm going to write this as theta 2 to the negative 2 sum of xi minus theta 1 squared over 2. Okay? So when I take the derivative of this, so I'm going to rewrite it, equals d theta 2 of negative n theta 2 to the negative 1 over 2 plus theta 2 sum of xi minus theta 1 squared over 2. So I'm going to take the derivative of that with respect to theta 2. And by writing it this way, it just saves me from using the quotient rule and all that mess. Okay? So this is going to be, I've got a negative here, So negative 1 times negative is positive, so I'm going to have n theta 2 to the negative 2 over 2. And this is a negative 2 here. Did I not? Yeah. So, yeah. Okay. So now, this is a constant with respect to theta 2. So it's just going to stay. So all I'm doing is taking the derivative of theta 2 to the negative 2. And so that is going to be negative 2, theta 2 to the negative 3, sum of xi minus theta 1 quantity squared over 2. So this 2 and this 2 cancel. And so this gives me n theta 2 negative 2. So I'm going to go ahead and put this in the denominator so I can find a common denominator. So this is going to be 2 theta 2 squared minus sum of xi minus theta 1 quantity squared over theta 2 cubed. So the common denominator is going to be theta 2 cubed. This is the second derivative, but I'm going to substitute in, I'm going to make a substitution here. I want to point out that note theta 2 hat is equal to 1 over n sum of xi minus theta 1 squared, okay, which is x bar. Is that what I'm doing? Yeah. So that means that sum of xi minus theta 1 squared equals n theta 2 hat. Okay? So now I'm going to substitute in, I'm going to change the thetas, theta 2s to theta 2 hats. And this, I'm being clever here so that I don't end up with a mess. When I see this, I see it's the same thing as theta 2 hat, except for a constant, which is n in this case. So there's no 1 over n here. So I can certainly write it in terms of theta 2 hat. That pattern is really important to making this easy. Otherwise, you're going to struggle through a lot of math, which that's your choice. Or sometimes you just don't see it, and that's all we can do when we don't see it. Okay, so this is going to equal n 2 theta 2 squared hat squared minus n theta 2 hat over theta 2 hat cubed, which is equal to n over 2 theta 2 squared hat, or hat squared, minus n over theta 2 hat squared, because this and one of these cancel. And so this is going to be, okay, so I can factor out, if this makes it easier for you, factor out n over theta 2 hat squared. And I end up with 1/2 minus 1. If that makes it easier for you to see, that this is half of this, the 2 down here. So this is going to be negative 1/2 of this. So negative n over 2 theta 2 hat squared, which is always less than 0 because n is positive, theta 2 is positive, theta 2 squared is positive, and this is a negative. Therefore, theta 2 hat is a max for theta 2. It's a maximum for, I'm sorry, not theta 2, for L of theta 1, theta 2. Therefore, theta 2 hat equals 1 over n sum of xi minus x bar quantity squared is the MLE of theta 2. And if theta equals theta 1, theta 2, then theta hat equals x bar, comma, 1 over n sum of xi minus x bar quantity squared. Okay? So I know this is a long problem, okay? And then closed. Okay. So, all right. So this is telling us that we have, this is a very important, this is the MLE for the normal distribution. This is theta 1 hat, this is theta 2 hat, and we're going to talk about this is not quite the standard deviation. Remember, 1 over n minus 1 sum of xi minus x bar quantity squared is the standard deviation. This is s squared. But this is not really s squared. This is what we would use for a population standard deviation calculation, okay? If you remember introductory statistics. All right, so that's it for this video. A very important problem. I hope you'll review it. Make sure you know how to solve it. If you have questions, come to virtual office hours. If you need help before then and can't wait, by all means, email me. I'm happy to help you. I'll help you as soon as I can. Please take care of yourself, and we'll see you next time.